Hey everyone, Adam the Tutor here, coming at you with the second part of our mass spring system problem. And in this part, we want to describe each of the cases of motion. Now, what I mean by each of the cases of motion is that if you'll notice, this gamma right here depends, well, here, I didn't, let me actually underline what I'm talking about. This gamma right here depends on both omega naught and gamma over 4, right? So clearly we have a couple cases to deal with, right? So let me switch to blue here. So case 1 is when, oh, here, let me write it out to the side. Omega naught is greater than, well, here, let me just do this. Gamma squared over 4, right? So this is the case when big gamma is positive, right? So it implies that big gamma squared is positive. So basically what that means is our complementary solution is going to actually oscillate, right? Because we have a frequency that is positive. Well, it's not that the frequency is positive. The reason why is because this frequency is real, right? So this right here, this gamma squared being positive implies that gamma is a member of the real numbers, right? So basically, we're going to have a spring that oscillates. It starts here. Let me graph here, right? So basically, what we're going to get. This is not going to be a great graph, but that's fine. This is x of t. Right? So at time t equals 0, the sine term will be 0, the cosine term will be 1, and we'll have that this will be, let's say x naught's right here, right? Right? So basically what'll happen is it'll go, and it'll oscillate, it'll kind of die down a little bit. So it'll look something like this, right? It may not be this dramatic. It depends on the dampening, the little gamma. But, it'll look something like this, right? It'll have this negative exponential envelope that kind of bounds it, right? Okay, so case 1 is the most straightforward of the 3 to deal with. So, now case 2. Case 2 is when omega naught squared equals gamma squared over 4, right? So what does that mean? Well, that means that our frequency is 0. Well, if our frequency is 0, that means that there's not going to be any oscillation, right? Because this sine term will be 0, this cosine term will be 1. So basically what that means is that our complementary solution becomes the following: x naught e to the minus gamma over 2. So basically what happens in this case is this. This is, well, I guess I really should be writing xc right here. Okay. Oh, didn't mean to do that. So basically, this is just going to be a negative exponential, which will look a lot like, just what we had, the envelope that I drew in case 1. So it'll go something like that. It won't go negative, but you get the idea. It goes to 0 fairly quickly. You'll have to forgive my artistry skills. I am I am not a student of the arts, although I would like to be. Okay, so that's basically what's going on with case 2. Pretty straightforward. Okay, now case 3. Case 3 is omega naught squared is less than gamma squared over 4. And what that implies then is that gamma squared is negative, which can only mean one thing. It means then that gamma is a member of the complex numbers, right? So basically what we're going to have going on then is there's going to be, well, let's begin with sine and cosine, right? What does it mean if gamma is a member of the complex numbers here? Well, here, and we'll assume we'll look at a purely imaginary gamma, right? Because that's kind of the best way to do it. So gamma is purely imaginary. So basically what that means is, well, first let's start with the Euler identity, right? The Euler identity is e to the I theta is equal, well, no, not sine, cosine. Oh, no, that was the wrong tool. Cosine of theta times I plus sine theta. So cosine theta plus I sine theta. Right? So if this theta is imaginary, then maybe we could rewrite it as, let's see. So theta is equal to I phi, maybe, right? So if theta is equal to I phi, then that means that this will be e to the negative phi, which will be equal to cosine I phi plus I sine I phi, right? So basically what this means is that whenever we have a complex number, a purely imaginary one, in this, in this guy right here, what that means is, or in one of the cosines or sines, what that means is that we're going to have a linear combination of this negative exponential. So basically, it's going to be something similar to this. It's probably going to die off faster since it's a linear combination of exponentials, and gamma here is greater than omega in this case. But so basically, you're going to get this behavior that dies off. It dies off very quickly, right? And the name of each of the cases escape me. I could be wrong. This, I believe, is underdampened. Underdamped, I guess I should say. This one is critically damped. Critically damped. And this one is overdamped. Okay. I'm sure this one is underdamped. I don't remember which one of these is which. I'm pretty sure this is correct. But the names don't matter. What matters is that you understand the behavior. So the main idea here is no oscillation occurs here. And no oscillation here. But here, there is oscillation. Oh, that should be an N. So we're happy with this guy, right? Okay, so I think that's all Part B asked us, right? Asked us, describe each of the cases of motion. Does oscillation always take place? Well, so yeah, I mean, oscillation does not always take place. It is dependent upon the relationship between this omega naught squared and gamma squared over 4. And yeah, so that's basically it for Part B. I kind of did it all in blue. I wasn't really planning to do that. But, you know, hey, it's fine. Break up the monotony of color that is going on. So, that is it for this video, and I will see you in Part C. Thanks for watching.